Hello everyone. Today we're going to discuss imaginary numbers and why they aren't actually imaginary. In fact, the term is somewhat misleading, and after today's presentation, I hope you'll view these numbers in a new light. We'll explore the topic from both a mathematical and a physics and engineering perspective. Imaginary numbers have been given a bad reputation, mostly because of their name. They're often introduced in math classes without a full explanation of why they're useful or how they're applied in real life. Today, we'll look at imaginary numbers through two lenses. The mathematical perspective, where imaginary numbers come from and how they work in equations. The physics and engineering perspective, how these numbers help us solve real-world problems like oscillations, waves, and signal processing. Let's begin with the mathematical perspective. When you're solving quadratic equations, like x squared equals -4, you run into a problem. The square root of a negative number doesn't exist in the real number system. But when we introduce the imaginary unit I, where I equals square root of -1, we can solve these equations and find solutions like x equals plus and minus 2i. So, imaginary numbers are actually quite useful in solving equations that have no real solutions. Now, let's talk about negative numbers. When you multiply a positive number by a negative, you're not necessarily changing the amount, but rather the direction. For example, if I give you $20, you have $20. But if I take away $20, you have negative $20, still a real amount, just in the opposite direction. This idea of flipping directions is important in understanding how imaginary numbers work. When you multiply a real number by -1, you are rotating that number by 180 degrees on the number line. Imaginary numbers take us beyond the one-dimensional number line and introduce a second dimension. When we multiply a number by I, we rotate that value by 90 degrees onto the imaginary axis. Think of the number line as a flat plane. Real numbers sit along the horizontal axis, and imaginary numbers sit along the vertical axis. This allows us to represent both types of numbers together in what we call the complex plane. When you multiply by I, you're rotating the number by 90 degrees. Let's take a look at how this works with the number 3. If we multiply 3 by I, we get 3i, which moves our point to the imaginary axis. But what if we multiply by I twice, or I squared? Since I squared equals -1, this means that after two 90 degrees rotations, we end up with a 180 degrees rotation, placing us on the negative real axis. Now, let's shift our focus to how imaginary numbers are used in physics and engineering. In these fields, imaginary numbers are not just abstract concepts, they are essential tools for modeling things like waveforms, oscillations, and alternating current (AC) circuits. For example, the voltage and current in an AC circuit can be represented as complex numbers, where the real part represents the magnitude, and the imaginary part represents the phase or direction. Even though we call them real and imaginary, these two types of numbers are part of the same complex plane. Imaginary numbers are not less real than real numbers, they just represent a different direction in the complex plane. Both real and imaginary numbers are important, and together they form complex numbers, which are essential for many advanced applications in math, physics, and engineering. Complex numbers are not just theoretical, they have many practical applications. One of the most important is in Fourier transforms, which are used in signal processing to analyze things like sound waves and electrical signals. Imaginary numbers also come into play when dealing with oscillations and rotations in physical systems, such as alternating current, AC, circuits or electromagnetic waves. Imaginary numbers are a powerful tool for solving equations, representing signals, and understanding physical systems that involve oscillations or rotations. They're not just abstract, they are real, measurable quantities that help us visualize and analyze more complex phenomena. Complex numbers are used in Fourier transforms and other practical applications.
In a world full of noise, we're searching for the sound, chasing shadows of the answers.